Hello everyone, I'm Mahmoud, a postdoc researcher in Ghent University, and I'm going to present Cactus, which is a top-down GPU benchmarking methodology using real-life applications. This work is done in collaboration with Professor Leven Eckhout. First, I'm going to explain how GPU benchmarking has been evolved over the previous decade. The purpose of using a GPU is to accelerate a specific part of a code that we call it a kernel. And this kernel has two basic properties. It should be data parallel algorithm, and it must be computationally expensive for CPU. In 2006, a technical report from Berkeley University discussed the landscape of parallel computing research. In this report, several problems have been discussed that have the capability to be accelerated via parallel computing. These problems are called dwarf, and they are basically used in traditional linear algebra and n-body simulation, and they have been also extended to emerging data parallel problems such as machine learning and graph workloads. Therefore, based on this picture, we have applications on the top and kernels on the bottom, and the idea is to develop essential computational kernels that can be used in applications. Based on this idea, several benchmark suites have been developed over the previous years, and they are focused on essential kernels rather than applications. We call this approach a bottom-up approach. Our survey in the past 10 years shows that Rodinia and Parboil are two well-known benchmark suites that have received more attention in academia compared to others. While they are simulator-friendly, they suffer from two problems. First, they are based on bottom-up approach, as we discussed earlier, or they are kernel-centric. And second, they lack machine learning applications. However, machine learning benchmark suites in the past few years have their own shortcomings. For example, they use bottom-up approach for machine learning operations, or they are complex at architectural level, or they lack modern machine learning libraries while they are used with simulators. Our observation shows that most of the traditional workloads have one or two dominant kernels. By identifying the dominant kernel, we are able to identify its resource bound and see if it is compute bound or memory bound. Then we can focus on performance bottlenecks in order to improve the efficiency. In this work, we introduce Cactus, which has a different benchmarking view. That is, we use a top-down approach and collect applications with multiple kernels. These applications use modern algorithms, and they are primarily used in HPC domain. Currently, Cactus includes 10 workloads. 3 workloads are related to molecular simulations, 2 workloads are related to graph analytics, and 5 workloads are related to machine learning applications. In the rest of the slides, we are going to use some analysis to show the difference between Cactus workloads and traditional workloads. This figure shows that the GPU time in Cactus workloads is distributed over multiple kernels. And in some workloads, we see that there is no dominant kernel. Here we see the result of roofline analysis for molecular and graph workloads. This figure confirms that these workloads have kernels with diverse resource bounds. For a better representation, we have highlighted important kernels in these workloads. As you can see, important kernels that together take at least 70% of the total GPU time have diverse resource bounds. The same result can be seen for machine learning applications, and with respect to the large number of kernels, they are composed of both memory bound, and compute-bound kernels. We also see here that important kernels in machine learning applications take less than 10% of the total GPU time. Therefore, we can say that the execution behavior in Cactus is more complex compared to traditional ones. We also use Pearson correlation coefficient method in order to find the correlation between key performance metrics and architectural features. And the result for Cactus and Parbo, Rodinia, and Tango are shown in this figure. We can see that there are stronger correlation between performance metrics and architectural features in Cactus compared to the traditional workloads. We also used FAMD method in order to build hierarchical clusters based on quantitative and qualitative variables. And the result for Cactus kernels and traditional kernels are shown in this figure. We can see that Cactus benchmarks cover a broader workload space compared to traditional ones. As a summary, Cactus provides a top-down view on GPU benchmarking by collecting real applications that have multiple kernels and diverse resource bounds. Workloads with codes and scripts are publicly available in GitHub and Zenodo. Thanks for watching.